So what we will start looking at today is what right, so what we call immediate RL, immediate reinforcement learning problems. So if you remember, I said there are many characteristics of a reinforcement learning problem, and one of those was that you get this evaluation from the environment. It could potentially be delayed, right? So I said you might actually lose a piece, very important piece in the middle of a chess game, but you get a reward only at the end, right? It's not like the final move you made is the one that causes you to lose. It could be somewhere along the way, right? So what we are going to do now is to actually consider a much simpler version of the problem, where we do not have the temporal nature to it, right? So we are not going to assume that the rewards or the scalar evaluation that comes from the environment is going to come at a farther time than when the action is actually performed, right? So I'm going to assume that as soon as you perform an action, right, you are going to get a evaluation, right, and that's it basically, right? So we're going to consider a much more simplified version of the problem, that is, at every time instance I'm required to pick an action, right? So at every time instant t, right, I pick an action at, right, and then I receive a reward rt, right, and that's it. My interaction is ended, right? So I can learn something from this interaction and go back and pick another action at time t plus 1, right? So that's why we call this immediate reinforcement learning problems, because the outcome is immediate. So as soon as I take an action, I get a reward, right? So what else is missing in my description here? There is no real input to the system, right? There is no state signal that the system is seeing. So all the input it is getting are the rewards, right? There is no state input to the system, right? So it's just solving the same problem again and again, right? So instead of thinking of it as not having a state, you could think of it as having, like, every time I give it the same input and I'm asking it to give me an action in response to that. So does it seem like a reasonable thing to have? Can you think of cases where this might actually be an appropriate model? So one example which people give is in drug testing, right? So I have a certain symptom that is presented to me, right, and I can choose one of 4 different drugs to treat that symptom, right? So at first I give drug 1. It may or may not cure the person. If it cures the person, then I get a reward. If it doesn't cure a person, I don't get a reward, right? But it could very well be that for a variety of reasons the person didn't get cured. It's not because that the drug 1 was not the right drug to give for this person, right, for these symptoms, but for a variety of other reasons the patient might not have been cured, right? So I can't conclude by just administering the drug once that the drug is ineffective for a set of symptoms, right? I have to keep trying the drug multiple times, right, before I can come to a conclusion that the drug is ineffective for a person, correct? Right. So for a certain set of symptoms, so it's like saying that, okay, there are multiple samples that I have in a lab, and each of them is exhibiting the same disease, right? Let's not talk about human beings administering drugs and killing them or something. You can think about samples in the lab, right? I'm going to add some drugs to that and see if that particular organism dies, right? When I add the drug, right? So it's essentially the same presentation as far as the drug testing goes, right? It's the same organism that I am trying to kill, same microorganism that I am trying to kill across all of these different instances, right? It's like the same state that is being presented to me over and over again. But then I have multiple choices that I could make, and as soon as I do the choice, I get a feedback saying, okay, yeah, the organism died or it didn't die, right? So I have to keep trying this multiple before I figure out which is the right drug to administer. Okay, good. Is that clear? So that gives you an example, right? So there are a couple of things which I kind of rolled into the example as well. So one of this is that the outcome can be stochastic. Right? So every time I take an action, right? So I need not be given the same evaluation back. Right? So I take a tissue sample, add a drug to it, right? So I might not succeed every time, right? So sometimes I will succeed, sometimes I might not succeed. So there is some kind of a stochastic nature to the outcome, right? So as a consequence of the stochastic nature, what did you have to do? I had to repeat things multiple times, right? So these are things which you have to keep in mind when we are talking about this kind of immediate reinforcement learning problems, that we are going to have stochastic outcomes, and then we'll have to think about repeating choices multiple times before we can be sure of the outcome, right? Is there anything else that was that would have been critical to the successful outcome of this? Let's say that I tried drug 1, okay, and the organism survived. Okay, so then can I keep using drug 1 for all the other organisms as well? Let's keep the problem simplified, right? Will say I have only 2 drugs, drug 1, drug 2. Okay, I take the first organism, give it drug 1, it survives. I take the second organism, give it drug 2, doesn't survive. Okay, now can I conclude that which one is more effective, drug 1 or drug 2? We don't know, but assuming it's one step. The survival, what we are looking for, not survival, what we are looking for. Not survival. I'm talking about microorganisms here, right? So I actually flipped it around, but nobody actually noticed it. So yeah, so I'm looking for non-survival of the microorganism, right? So in this case, drug 2 appeared to be more effective than drug 1, right? So that doesn't mean I can keep giving drug 2 to all the other samples. Right? I need to actually go back and try drug 1 a few times, right? So this is the exploration. Right? I was telling you about exploration in the previous class, right? This is the exploration here. Right? I have to do exploration, right? So the critical thing here that even the simple case of this immediate reinforcement learning introduces to is the need for exploration, right? But can I just keep exploring? Can I just keep giving random drugs to each of those samples? And at some point I have to stop, right? I'm interested actually in killing those microorganisms, right? At some point I have to stop and decide, okay, here this is the actual drug that is going to kill the microorganisms, and I have to start giving that drug, right? This need not be an explicit point where I stop, we will see as we go along, but I am interested in eventually exploiting the knowledge that I am acquiring about this, the whole system, right? So either I explore or I have to, at some point I have to stop and start exploiting. So there is this inherent tension between exploration and exploitation. Okay, they are in some sense at loggerheads with each other, right? If I stop at some point and say, okay, I have know enough about the system, and then I start exploiting, then I necessarily have to stop my exploration, right? But then if I don't explore enough, I will be exploiting a poor solution, right? So this exploration exploitation, so sometimes people call it a conflict, sometimes it's called the explore exploit dilemma, right? So should I explore or should I exploit? So that's essentially what this immediate reinforcement learning problems captures for. Okay. So this is a very crucial question in reinforcement learning. So we will look at this immediate reinforcement learning problems in a little bit of detail, so that it will motivate some of the other things that we will do later when we move to the full oral problem, right? And so what I will do, which is slightly different from what is there in the textbook. So how many of you have actually looked at the textbook? Good. See, I didn't ask how many of you have read the book, right? So what I will do that's slightly different from the book, and I've still not decided whether it will be for both versions of the course, is talk a little bit more about some of the theoretical questions that people are interested in addressing in the immediate oral setting, right? The book just gives you a very, very algorithmic, very prescriptive viewpoint of this, right? This is, oh, here is how you solve the immediate reinforcement learning problem, right? It doesn't go beyond that. It doesn't give you anything about right. So why do people solve it the way they do, right? So I'll go a little bit beyond that and try to give you some intuition in that, mainly because that seems to be a very active area of research nowadays in reinforcement learning, and many of the ideas that people are using there are also being transferred to the full reinforcement learning setting, the one with all the delayed rewards, the states and things like that, right? So a lot of ideas from the research in this immediate RL setting is also being used in the full RL setting. So I want to introduce you to those topics, right? Yeah. So despite the makeup of the class, right, which is predominantly undergrad, this is a graduate level course, right? So I want to introduce people to research questions and other things. Yes, there have been demands for to actually teach an advanced RL course at some point, and I know at least one person who will take it. So I'm going to try this now. Every class I'm going to make people turn and look at you at least once. I managed to do that last class. So anyway, so go back. So we'll look at a little bit of formalism on this, right? So what I'm going to assume is that I have a set of actions A, which I will index by 1 to n. So action 1 could be anything, right? I'm just giving them arbitrary numbers, 1 to n. It could be drug 1, drug 2, drug 3, right? Or it could be add 1, add 2, add 3, whatever it is. Just 1 to n is what we will denote it as, right? And each action, when I pick that action, right, gets a payoff. It's an evaluation. So I'm going to be using these terms interchangeably, right? Reward, payoff, evaluation, cost. So all of this denote the same thing, that dotted line that came in my box diagram, right? So depending on what literature you come from, you use different names for it, right? So the reward typically comes from, guess, psychology, right? Cost comes from control theory, optimization, yeah. Payoff comes from economics, and what was the last thing I said? Evaluation comes from optimization. Oh, okay, fine. So depending on which background you come from, you give it different names, right? And so I'll use them interchangeably. For example, for most of this literature, I'll be using payoffs because a lot of the work has been done in the OR and economics community when they are trying to analyze these kinds of problems, right? So when I actually select an arm, I select an action, right? What's going to happen is that I'll get a reward or a payoff sampled from some unknown distribution. So what do I mean by that? Stochastic. But what do I mean more? I mean, right? This is something which I found people have difficulty. So some people at least have difficulty when I say it's sampled from a distribution. So what I mean is the following. Okay, let's keep it simple so that people can conceptualize it. So associated with each action, let us say that I have a coin. Okay, associated with each action there is a coin, okay, that has some probability of coming up heads and some probability of coming up tails. Okay, so let's some probability p of coming up heads. So let's say I pick action 1, then there is a probability p1 of coming up heads when I toss the coin, right? And I'll say that if the coin comes up heads, okay, I'll give you a payoff of 1. If the coin comes up tails, I'll give you a payoff of 0. Right? So every time I select an action, I'm going to toss this coin. So depending on whether it comes up heads or tails, I'll give you either a 1 or a 0. Right? So the payoff that I'll get every time I select that action is not the same. Right? But what is same? The coin. Right? If I select action 1, I'll always toss coin 1. If I select action 5, I'll always toss coin 5. Right? I'm not changing these coins. Okay. Is it clear? Does it make sense to people? Right? I've not changed the coins will be the same, right? But every time I pick a action, I'll toss that coin and I'll give you the payoff or reward corresponding to the outcome of the coin toss. Okay. So if I say that the probability of reward for picking action 1 is 0.8, what does it mean? The probability of heads of the associated coin is 0.8. Right. In this case I can go further, I can also say something else. I can say that the expected payoff of picking action 1 is 0.8 as well. Right, because with probability 0.8 I will get a reward of 1, with the probability 0.2 I will get a reward of 0. So if I take the expectation of this, it will be 0.8. Right. Do people understand this now? So when I say select an arm, select an action, I will tell you why I keep calling it arm in a second, and then I will keep calling it arm. So when I select an action, right, then I am going to toss a coin, right, depending on the outcome of the coin I am going to give you reward. This is something which you should remember when you are actually going and implementing these things, right. So I have had people do all kinds of weird things, right, and make sure that you remember what I mean when I say you sample from a distribution. Okay, great. So now I gave you the simple example of tossing a coin. I could actually have any complex distribution, right. So if I toss a coin, what is the distribution I am sampling from? Bernoulli, right. I could have other kinds of distributions. I could have a Gaussian distribution, let us say. So now what does it mean? For every action I choose, okay. So for action 1, that is going to be a like some kind of a Gaussian distribution, right. And so what is the axis here? X axis here? The payoff or the reward, right. The x axis the payoff or the reward, and the y axis is the probability that you will see such a payoff, right. So that is the most probable payoff. That also happens to be the, for Gaussian, that also happens to be the expected payoff, right. So how will I sample from a Gaussian? Pick a random number and?
Pick a random number between
0 and? Anyone else? How will you sample from a Gaussian?
Log transformation.
Okay. What do you do then? People who are in my minor, I told you how to do this in the class. Okay, a little bit more efficient way of doing it.
Define a Gaussian over a mean and a variance.
Yeah, and then what do you do? Don't tell me you use MATLAB.
Sir, MC.
No man, it is your role. You know too many terminology, just keep throwing them around. What does the MC stand for in?
Markov check.
Then there are two MCs.
Monte Carlo.
Then you just told me Monte Carlo. I said give me something more efficient, and then he keeps saying another Monte Carlo method. What is that? No one? Oh come on. Fine, okay, Pallavi, you tell me.
CDF and
So the guys who were in the, you guys were there in my minor thing, right? So I actually told you how to sample. Do you remember? I said, so I did this with a discrete distribution, and then I told you how to do this with continuous distributions as well. Can you give them a write-up on Moodle? Okay. So basically the idea is you generate a random number, right, between 0 and 1. Generate a uniform random number between 0 and 1, right, and then keep integrating the area under the curve. So what is it called? The CDF, right, and then when the CDF reaches that random number you generate, so that is the number you sample. Okay. Does it make sense? Okay. So this is a complete aside. Okay. Let us say that I have 4 possible outcomes, right. I want to generate one of those 4 outcomes at random, right. So the probabilities are P1, P2, P3, P4. How will I do that? I will generate a uniform random number between 0 to 1, right? No. So I will see if the number is less than P1. If the number is less than P1, I will generate outcome 1. If the number is between P1 and P2, I will generate the outcome of 2. If the number is between P2 and P3, I will generate the outcome of 3. If the number is between P3 and P4, is that correct or wrong? should be between P1 and P1 plus P2. Okay, it should be between P1 plus P2 and P1 plus P2 plus P3. So it should be the cumulative sum. Right? It should be the cumulative sum, previous cumulative sum and the next cumulative sum. If it lies between that, then that is the outcome I'll generate. Right? So if it's less than P1, I'll generate 1. If it's between P1 and P1 plus P2, I'll generate 2. If it's between P1 plus P2 and P1 plus P2 plus P3, I'll generate 3. If it is between P1 plus P2 plus P3 and 1, I'll generate 4. Right? Don't tell me P1 plus P2 plus P3 plus P4. Okay.
Sir, in that method, we can't do it based on CDF because we don't have an inverse for Gaussian. We don't exactly get the
So you can simulate the CDF for the Gaussian, right?
simulated.
Yeah. So there are ways of doing it, right? So there are ways of doing this. So you can do this for any probability distribution for which you can define the CDF. Right? Not just Gaussians, not just discrete. So the discrete case, it's very clear, right? So what you are doing is essentially adding up the probability. So and whenever you hit that number, you say that's the sample that you have drawn, right? In this case, you just do this for the Gaussians. Okay. So this is what I mean when I say sample from a probability distribution. Again, right? It's not the most probable outcome. Right? When I say sample from this Gaussian, I have actually seen people implement. Okay, that's the reason I keep reiterating this. People actually form the Gaussian and then keep returning the value that has the highest probability. Right, so please don't do that. Of course, if you are using MATLAB or something like that, you don't even have to think about it. You can just say rand n and then it will give you a sample from a normal distribution, which is what Shubha was going to tell you, is the way to sample from a Gaussian. But this is what it does internally, right, and to give you the sample. Having said this, now you can go back to using rand n. Yeah. You had a question? No. Okay. Fine. So going back, associated with each of these actions, right, I am going to have some distribution from which the payoff is being sampled. Okay, is that clear? And these distributions, I am going to assume, at least initially, will be fixed for the duration of the experiment. For duration of the learning, these distributions will be fixed. Like I said, you don't change the coin, you don't change the Gaussians also. Okay. Now, if I knew the Gaussians, right, or if I knew the coin, if I knew the probability with which the coin will turn up heads, right? So how will I solve the problem? There is no problem, right? I just pick the action that has the highest mean, right? Highest mean for the Gaussian or the highest P1 for the coins, right? Whatever it is, the highest expected payoff. I just pick that arm. Pick that action, right? So the challenge comes when I don't know the distributions. All I know is there is some distribution which I am assuming is fixed, right, according to which the payoffs are generated. I don't know the distribution, so I basically have to figure out the distribution, right, and then pick the action. Pick the action corresponding to that, right? So is that clear? So for each of these actions, right, for each of these actions, I am going to assume that there is a true expected payoff, which we will denote by Q star of A. Right, so A is the action, so Q star is a function that will give me the true expected payoff of action A, right. So in the case of the coins, Q star of 1 will give me P1, which is the probability of heads, right. Q star of 2 will give me P2 and so on and so forth. In the case of Gaussians, Q star of 1 will give me mu1, right. Q star of 2 will give me mu2 and so on and so forth. So that's essentially what the Q star function is. This is again unknown to me, right. If I know Q star, I am done, right, my problem is solved, right. But this is the assumption we are going to make. So we have a set of actions A and we have a set corresponding Q stars that we don't know about, right.